In this video, we shall look at a few problems associated with crucial concepts in rotational motion. Problem 1. A cyclist starting from rest moves with a constant acceleration of 1.5 radian per second squared. The wheel's radius is 40 centimeters. Find the cyclist's linear acceleration. What is the angular speed of the wheels as the cyclist reaches 10 meters per second? How many radians have the wheels turned through in that time? And finally, how far has the cyclist traveled? The first thing we notice is that this is a motion with constant angular acceleration, namely 1.5 radian per second squared. So we are dealing with rotational kinematics. Another thing that is being tested here is the relationship between the angular variables and the linear variables. So let's do part A. What is the cyclist's linear acceleration? So linear acceleration is A, the unit of which is meter per second squared. Now the linear acceleration here is related to the angular acceleration in a following manner. So this is the angular acceleration, and this is the radius of the wheel. Suppose this is the wheel and the radius is r, and it's turning like that. If the wheel is turning faster and faster and faster, then the direction of this angular acceleration vector is the same as the direction of the angular velocity vector. In this case, the direction of the angular velocity vector, because of the direction of that rotation, is coming out of the board. So the direction of alpha here must also be coming out of the board, because it's a positive 1.5, so the wheel is turning faster and faster. So let's proceed to calculate A. Now we know the radius is 40 cm, so let's convert that to meter, 0.4 meter, and alpha is 1.5 radian per second squared, and you get 0.6 meter per second squared. So that is the answer for part A. Now part B. Find the angular speed of the wheels as the cyclist reaches 10 meters per second. So that 10 meters per second is the linear speed, and it's related to the angular speed in the same way as an angular acceleration is related to the linear acceleration. So since we are interested in angular speed here, it is the linear speed over the radius. Now we know the linear speed is 10 and the radius is 0.4 meter, and you get 25 radian per second. Now part C. How many radians have the wheels turned through in that time? So let's assume that we start timing at that state. So here it starts from rest, so this angular speed is 0 radian per second. And let's assume the wheel starts to turn and it accelerates with an angular acceleration of 1.5 radian per second squared, and it gets to that point. Let's call that the final point. So at the point of which the angular velocity or the angular speed is 25 radian per second. What we want to know here is what is the angular distance, or displacement in this case, covered. How many radians? So since we know the final angular speed, we know the initial angular speed, which is 0. We know the angular acceleration, and we want to determine the angular displacement. We can use one of the rotational kinematics equations here, which is the square of final angular speed minus the square of the initial angular speed equals 2 times angular acceleration, which is constant, times the angular displacement, which is what we want to find. So the final angular speed is the answer from part B, 25. Don't forget to square that. The initial angular speed is 0 because it starts from rest, so 0 squared equals 2. Alpha is 1.5 delta theta, and we can get delta theta, which will be 208 radians. Now finally, part D. How far has the cyclist traveled? Meaning, what is that arc length? Let's call it S. So the arc length is given by the radius times the angular displacement. So which we know in this case. So 0.4 is the radius and angular displacement is 208 radians, which is 83.2 meters. And that solves the problem. Problem 2. A blade turns at an angular speed of 300 rev per minute. Let's say like that. So this is the blade. And it is turning about an axis that's passing through this point, and it's coming out of the board. What is the angular speed in radian per second? We know the angular speed in rev per minute, that is 300. So let's change a rev into radiant. So 1 rev is 2 pi radiant. So that means you have to multiply the top with 2 pi. Now you have to change minute to seconds. And each minute contains 60 seconds, which will give you 31.4 radiant per second. Part B, given that the blade has a length of 1.8 meters, so this length is 1.8 meters, that is also the radius of rotation, calculate the arc distance of the tip of the blade traced out in 250 seconds. So let's say, just as an example, in 250 seconds, the blade gets to that point. So that means that is the arc distance that we are looking for. And to get that, we need to know what is the angular displacement. So we can determine the angular displacement quite simply as the constant angular speed, which we have calculated in part A, times the time it takes to cover that distance. So omega is 31.4, t is 250 seconds, and that's going to give you 7,850 radiant. And now we can get the arc length. It is just the angular displacement times the radius. So the radius is 1.8 meters times 7,850 radians, and that's going to give you 14,130 meters. And that solves the problem. Problem 3. A wheel turns with a constant angular acceleration of 4 radian per second squared. So this is another example of rotational kinematics. If the angular speed of the wheel is 2 radian per second at t equals to 0 seconds, find the angular displacement of the wheel between t equals to 0 and t equals to 2 seconds in radians. So let's do that first. So let's assume this is the wheel turning like that. We shall use the horizontal line as the reference line, and let's measure the distance and set the t equals to 0 seconds there. So let's assume that point at the tip of that wheel, which is at t equals to 0 seconds, is right here, and it has rotated all the way to this point at t equals to 2 seconds. And the angular displacement that we are interested in is that angle. Let's call it delta theta. So what we know here, we know acceleration. We know that at t equals to 0 seconds, the angular speed is 2 radian per second. So that is like the initial angular speed. We also know the time interval, for the point to travel between that point and that point, that is 2 seconds. And what we are interested in is the angular displacement. So one of the equations of rotational kinematics that enables us to determine that is the following equation: half alpha t squared plus omega I t. Alpha is 4, that's given right there. T is 2 seconds, so you have to take the square of that. Omega I at t equals to 0 is also 2, so 2, and t is 2. And you will get 12 radians as an answer for part A. Part B. What is the angular speed of the wheel at t equals to 2 seconds? So at t equals to 2 seconds, let's assume that the angular speed there is omega f. So omega f equals omega I, the initial angular speed, plus alpha t. So this is another equation of rotational kinematics. So omega I is 2, the angular speed at t equals to 0 seconds, that is, plus alpha is 4, and since we are determining the angular speed at t equals to 2 seconds, so t is 2, and you'll get 10 radian per second as the answer for part B. Part C. What is the angular displacement of the wheel as the wheel's angular speed doubles from the answer in part B? Now what that means is, now let's assume, because the wheel is rotating with an angular acceleration of 4, at some point its angular speed will double the value that we found in part B, namely 20 radian per second. So let's call that omega f. And this 10 is like your omega I, the initial angular speed. As the wheel makes its transition from this angular speed to that angular speed, it has to cover certain angular displacement. What is that angular displacement? That's what we want to determine. And we can easily calculate that using another rotational kinematics equation, that is omega f squared equals omega I squared plus 2 alpha angular displacement. Omega f is 20, so 20 squared. Omega I is 10, so 10 squared, plus 2. Alpha is 4, it's given. Delta theta, and you can calculate delta theta, which will turn out to be 37.5 radian. We can also express this answer in the number of revolutions, or number of turns. That is just 37.5. 1 ref is 2 pi radians, so divide that by 2 pi, which will give you 6 revolutions. That means it takes 6 turns or 6 revolutions for this wheel to speed up from 10 radian per second to 20 radian per second. That's what it means. Thank you for watching.